Isaac Newton stands as a monumental figure in the history of science, whose intricate analyses and pioneering formulations laid the bedrock for modern physics and mathematics. His work, replete with rigorous mathematical proofs and deep empirical insights, exemplifies the intellectual daring of an era where classical mechanics was both born and refined. In this presentation, we explore Newton's contributions with an advanced technical lens, delving into complex phenomena such as gravitational theory, the dynamics of celestial mechanics, and groundbreaking innovations in calculus and optics. We will examine the technical rigor of his Philosophiæ Naturalis Principia Mathematica, his elaboration of the laws of motion, and the sophisticated analytical methods he harnessed to unify terrestrial and astronomical phenomena. We also explore the broader context of his achievements, his intensive alchemical research, his incisive study of biblical chronology, and his unconventional approach to religious orthodoxy. An expert-level appreciation of Newton requires an understanding of the nuanced interplay between theoretical modeling and empirical data, and this script is designed to reveal the subtleties of his methodologies and the mathematical elegance behind his discoveries. Join us as we navigate through Newton's intellectual journey with an emphasis on technical depth and rigorous quantitative analysis. This journey is enlightening indeed. Born at Woolsthorpe Manor in Lincolnshire on Christmas Day, 1642, Julian calendar, Isaac Newton's early life was marked by both extraordinary potential and significant personal hardship. His father's death prior to his birth set the tone for a childhood shaped by loss and resilience. Raised initially by his mother, Hannah Ayscough, and later by his maternal grandmother, Newton was exposed early to a unique blend of care and neglect. This environment likely contributed to his introspective nature and precocious questioning of natural phenomena. Even in his infancy, anecdotal reports suggest that he was notably small, a detail that has since become part of his fascinating biographical lore. The separation from his mother after her remarriage also left an indelible imprint, propelling him towards an independent quest for understanding. Such formative experiences provided the early conditions that would, much later, foster his relentless curiosity and drive to uncover the fundamental laws governing the universe. Today, historians and scientists alike continue to analyze these subtle clues from his childhood, recognizing the profound influence early life adversities can have on nurturing a mind capable of revolutionary insights. Each detail of his formative years invites rigorous scientific inquiry into the nature of genius indeed. During his formative years, Isaac Newton attended the King's School in Grantham, where his intellectual versatility began to manifest. Enrolled between the ages of approximately 12 and 17, Newton encountered a rigorous curriculum that emphasized classical studies such as Latin and ancient Greek, while subtly introducing him to the early concepts of mathematics and natural philosophy. At a time when education predominantly focused on rote memorization of classical texts, his inherent curiosity drove him to construct ingenious devices and solve complex problems independently. Newton's early projects, including the construction of sundials and mechanical models of windmills, reveal a nascent understanding of geometry and the principles of engineering. These hands-on endeavors were not mere child's play. They were precursors to the sophisticated experimental techniques he would later employ in his groundbreaking work. Additionally, the challenges he faced, including conflicts with peers and overcoming bullies, seem to have sharpened his resolve and concentration, fueling his intellectual ascendancy. Mentors and educators at the King's School recognized his potential and encouraged him to extend beyond traditional learning. This period in Grantham laid the groundwork for a disciplined approach to scientific inquiry characterized by meticulous observation and rigorous experimentation. The fusion of classical education with practical application not only fostered Newton's analytical skills, but also instilled in him the confidence to question established norms. His ability to visualize complex phenomena and translate them into quantitative problems was already in development, setting him apart from his contemporaries and paving the way for his later revolutionary theories. The blend of structured learning and creative exploration at the King's School represented an essential phase in Newton's journey toward becoming one of history's most innovative scientists. This phase not only enriched his theoretical framework, but also catalyzed an enduring passion for analytical precision and innovative experimentation beyond all measure. Newton's academic tenure at Trinity College, Cambridge, marked a turning point defined by rigorous scholarship and the integration of classical and emerging scientific paradigms. Securing his admission in June 1661, Newton initially served as a subsizar, performing valet duties before earning a scholarship that provided him with the resources to deepen his studies. The curriculum at Cambridge was deeply rooted in Aristotelian thought, yet it also exposed him to revolutionary ideas from Descartes, Galileo, and Thomas Street, ideas that were radical in their departure from medieval perspectives. Newton methodically documented his queries in a series of questiones, where he interrogated the mechanical philosophy prevailing at the time. The closure of the university in 1665 during the Great Plague, far from being a setback, became an unprecedented opportunity. Within the seclusion of Woolsthorpe, Newton embarked on an intense period of self-directed study that became legendary. During these golden years, he not only delved into calculus and optics, but also synthesized mathematical techniques that bridged numerical methods with theoretical dynamics. His work during this interval exhibits a profound confluence of rigorous formalism and innovative empirical strategy, challenging entrenched scientific dogmas. The blend of systematic inquiry and creative experimentation allowed him to develop methods such as the generalized binomial theorem, which would later serve as a precursor to the calculus. Scholars today recognize that the analytical skills honed during his Cambridge years were instrumental in shaping the later breakthroughs in his career. Newton's notebooks from this period continue to be a subject of exhaustive study, revealing a depth of thought and a meticulous approach to problem-solving that exceeded the norm. His intellectual maturation at Cambridge set the stage for a lifetime of transformative contributions to the domains of mathematics, physics, and astronomy. During this period, Newton engaged deeply with theoretical problems that required not only pure mathematical insight, but also an astute sense for experimental validation. His work in developing concepts that merged algebraic techniques with geometric intuition prefigured much of modern analytical science. Through relentless inquiry and self-driven research, he laid a robust framework that remains central to studies in dynamic systems and physics. During the infamous plague years of 1665 to 1667, while many scientists were confined by the social and institutional constraints of their day, Newton experienced an unparalleled period of intellectual liberation at Woolsthorpe. In seclusion, he transformed isolation into a crucible for his most radical ideas, laying the foundation for many of his later triumphs. It was here that Newton's mind navigated the complexities of infinitesimal differences and the convergence of series, anticipating the formal development of calculus. His exploration of optics led him to dissect the nature of light, employing prisms to reveal that white light was a composite of a spectrum of colors. Moreover, his analytic approach to gravitational forces allowed him to mathematically deduce the elliptical orbits of planets, effectively reconciling the mechanical motions observed in the heavens with the terrestrial laws. Amidst these innovative breakthroughs, Newton revisited classical problems with fresh insight, leading to the formulation of the generalized binomial theorem, an achievement that underscored his ability to extend mathematical principles beyond conventional limits. His notebooks from these years contain intricate diagrams and dense calculations, evidencing a rare synthesis of empirical observation with abstract reasoning. The rapid pace of his discoveries, driven by a combination of innate genius and a disciplined experimental spirit, reshaped scientific thought entirely. Each breakthrough was quantifiably profound. For instance, his formulation of gravitational laws provided predictions that later matched astronomical observations with astonishing precision. Newton's creative process during this period was not simply iterative, but transformative, blending rigorous mathematics with innovative experiments in ways that challenged and ultimately transcended established scientific methodologies. The golden years at Woolsthorpe stand as a testament to how isolation, far from stifling creativity, can serve as a fertile ground for revolutionary scientific innovation. His work during this era is studied in depth to understand the algorithms and methods that continue to influence modern physics and applied mathematics. Moreover, contemporaneous accounts and modern analytical reviews reveal that Newton's work during these solitary years was marked by an extraordinary quantitative precision. His experiments were characterized by measurements and computations that anticipated many later scientific breakthroughs. Every equation and geometric insight was crafted with an attention to numerical detail that continues to challenge expert validation even today. This period remains a focal study in the evolution of experimental mathematics, showcasing Newton's uncanny ability to transform theoretical speculation into precise, verifiable models that have echoed through centuries of scientific advancement with excellence. In 1687, Isaac Newton published his magnum opus, Philosophiæ Naturalis Principia Mathematica, a work of such mathematical and conceptual depth that it redefined the very framework of classical mechanics. Within its pages, Newton formulated the three foundational laws of motion, thereby establishing the principles that govern both terrestrial objects and celestial bodies, a synthesis that had eluded previous scholars. The first law introduced the concept of inertia, a radical departure from Aristotelian thought, asserting that a body remains in uniform motion unless acted upon by an external force. The second law provided the mathematical formulation F equals ma, linking force, mass, and acceleration in a quantifiable manner that remains a cornerstone of physics. The third law, stating that every action has an equal and opposite reaction, offered profound insights into the reciprocal nature of forces, culminating in celebrated studies such as the two-body and three-body problems. Newton's derivation of Kepler's laws from these principles not only validated heliocentric models of the solar system, but also offered predictive power over phenomena including tidal forces, comet trajectories, and the precession of the equinoxes. His mathematical descriptions combine geometrical rigor with algebraic techniques, cementing a foundation upon which modern physics is built. The Principia's influence extended beyond simple motion. It heralded a new era of scientific inquiry, where empirical data and rigorous mathematical modeling intertwined. Detailed quantitative analyses and refinements in numerical integration, as evidenced by the Newton-Cotes formulas, emerged from his approach to continuous systems. His work represented an intricate ballet where calculus and geometry danced in harmony, and every theorem was supported by precise computations and experimental corroboration. Advanced scholars continue to scrutinize Newton's proofs and computational methods, drawing inferences that inform current research in dynamic systems, numerical methods, and even astrophysics. The enduring legacy of his Principia lies in its methodical blend of theoretical insight with experimental verification, setting an exemplary standard for scientific pursuits across centuries. Newton's comprehensive approach in the Principia demonstrated his capacity to quantify the natural world. Every derivation was taken lightly. Rather, it involved extensive computations and geometric constructions that required intellectual rigor. His integration of calculus concepts, although not formally recognized as such until later, provided a framework for continuous change that was unprecedented. The meticulous balance between hypothesis and empirical observation in his work established protocols for experimental validation that resonate in modern research laboratories. Moreover, his systematic use of series expansions and limit processes anticipated methods fundamental to mathematical analysis. Through these innovations, Newton not only refuted long-standing philosophical misconceptions, but also laid the cornerstone for a scientific revolution. Today, his work continues to be dissected, with experts unearthing nuanced interpretations that reveal deeper layers of mathematical sophistication and rigorous empirical support. Newton's extensive body of work transcends the formulation of gravitational theory, significantly advancing the fields of optics, calculus, and mathematics. In optics, his construction of the first reflecting telescope revolutionized observational astronomy, while his detailed study of light demonstrated that white light is composed of a spectrum of colors dispersed by a prism. This discovery not only transformed existing theories of light, but also laid the foundation for subsequent innovations in spectrometry and laser physics. In the realm of mathematics, Newton's development of infinitesimal calculus, concurrently with his intellectual rival Leibniz, provided a powerful tool for modeling continuous processes. His methods, though initially presented in geometric form, evolved to include analytic techniques that allowed for the generalization of the binomial theorem to any real exponent. Moreover, his work on power series and numerical integration, exemplified by the Newton-Cotes formulas, pioneered approaches that remain integral in modern computational methods. Newton's innovations in regression analysis and the calculus of variations further illustrate his enduring impact on mathematical sciences. His contributions in these areas continue to be studied and applied in both theoretical research and practical problem solving, offering rigorous frameworks that intersect with contemporary fields such as numerical analysis and fluid dynamics. The precision and depth of his mathematical investigations are reflected in the persistent relevance of his work in various scientific disciplines. His pioneering methods have laid the cornerstone for innovative problem-solving strategies that are indispensable in advanced research, high-performance computing, and the rigorous analysis of complex systems, pushing the boundaries of scientific inquiry. Isaac Newton's life was not solely defined by his scientific achievements. It was equally marked by his unconventional religious views, political engagement, and administrative acumen. Deeply introspective yet unorthodox, Newton privately rejected the doctrine of the Trinity, while publicly conforming to the Church of England, a stance that allowed him to navigate the complex religious landscape of his time without compromising his intellectual work. His theological inquiries and biblical chronologies, though largely unpublished during his lifetime, have since emerged as subjects of serious academic research. Politically, Newton aligned with the Whig Party, serving brief terms as a member of Parliament for Cambridge University, where he applied his analytical rigor to legislative affairs. Furthermore, his long tenure at the Royal Mint, where he served as warden and subsequently master, showcased his commitment to precision and integrity. At the Mint, his introduction of measures to enhance the accuracy of coinage and combat counterfeiting exemplified his methodical approach to practical problems. Newton's administrative reforms not only stabilized British currency, but also provided a model for modern financial oversight. His multifaceted career thus embodies the synthesis of scientific inquiry, political pragmatism, and effective governance, reflecting the complexity and breadth of his intellectual pursuits. Undeniably profound. Newton's unparalleled contributions have forever altered the trajectory of scientific thought and practice. His rigorous methodologies and groundbreaking discoveries continue to inform contemporary research, from the fundamental principles of motion to advanced computational techniques in numerical analysis. By bridging empirical data with sophisticated mathematical modeling, he established a paradigm that endures in every corner of modern physics and engineering. The legacy of his work is evident in the ongoing evolution of these fields, where his theories have been extended, refined, and validated through centuries of experimental inquiry. Beyond his scientific achievements, Newton's wide-ranging interests in theology, alchemy, and political affairs underscore the interconnectivity of knowledge across diverse disciplines. His life serves as a profound reminder that intellectual curiosity, disciplined inquiry, and innovative thinking can yield transformative insights. As experts continue to analyze the depth of his contributions, Newton remains a beacon for those committed to pushing the boundaries of what is known. His enduring influence is an invitation to embrace complexity, seek rigorous analysis, and apply creative problem-solving to the most challenging questions of our time. In sum, Newton's legacy not only paved the way for modern science, but also continues to inspire exploration and thinking across realms of